So last time we were talking about El-Jamal crypto systems, which play important role. And just to repeat, so we are working in this under the assumption of discrete log security. And there is usually for public key cryptography, you need a one-way function. And the one-way function here is modular exponentiation, modulo the prime number. And we are using that by taking a message here for the encryption and take one message and produce two messages. So we get an overhead of factor 2 for the encryption. And we produce two messages. The first one is using this one-way function, but now we're using it with a new random number. So the first number is basically, again, completely random. But we have some knowledge about that. And we use it by multiplying the message with the public key to the same power. And the public key is also using this exponential function. Now, for decryption, we can use the fact that we can compute that this g to the x can be recombined to g to the x to the k, and so getting y to the k. And so we can use the first part of a message here, multiply with the second part of a message, of course, taking the inverse before, and then we get the message back, which is half the size again. So that was the idea. And this El-Jamal encryption has a lot of nice features, especially since compared to RSA, for example, we are working with a prime number which is not secret. So we can really publish this prime number. Also, we're using this generator, which is not secret. So, so basically, we could have a lot of people working with the same tools. And if you want to participate and do something and maybe combine messages, the only thing you have to do is make your own secret key, which is also very easy. You just pick a random number. And that's it. And when you do this multiplication, and this is a very nice tool, which allows us to do even more than encryption and decryption. Now, when we talk about El-Jamal encryption, so usually it is synonymous with elliptic curves. Although elliptic curves work in a completely different way than this modular exponentiation, modular prime number. And but the thing is that the operators that elliptic curves give us are the same. So we end up having a completely different crypto function for which we can basically also do El-Jamal encryption. It's just that the operation have a different meaning and we can still use it. So that's the connection. If you see that some codes are saying, oh, you want to El-Jamal or you want to have elliptic curves, and you can switch and you can usually exchange them. Okay. So this is a semi-homomorphism, something we'll have to use later. Now we'll repeat some things for the elliptic curves cryptography. First of all, for the motivation to do is that we think that elliptic curves work with smaller key sizes because operation is more complicated. And so these elliptic curves come from a lot of mathematical background which was developed in the 19th century or beginning of the 20th century, which was more in the field of analysis. And so researchers were looking around in the end of the 20th century and looking for schemes which we can harvest to have public key cryptography. And so they found these elliptic curves which have a very nice property because they can build an abelian group. So Abel is a German mathematician. And in this abelian group, we can work and find public key crypto systems. But if you look from a historic point of view, this goes this discussion about these kind of polynomials goes back a long time. And it started with quadratic equations and cubic equations, which the solution of it, we completely understood only until the 16th century, which was the area of Renaissance. And these guys, Tartaglia, Cardano, Ferrari, were all in this northern Italic part where we have city-states, and basically science took off again after the ancient period. So this was a flourishing area where science was rediscovered, reading imported texts from Arabic countries, and they're also making progress in mathematics. So last time we tried to repeat that. So I think Sebastian Klein, is he here somewhere? So he gave me a link to this thing. So this tool, which we can use for that to see what's happening. So since we are not allowed to use Mathematica here on these things, so I haven't checked if it works. So this is a parabola, so you can play with that thing. Okay, so this is a lot of fun. So it goes up and down, and you can move up and down. That's if you have the last parameter going up and down, and this is the middle parameter, which does very strange things here. But if you look at this parabola, basically it only has one kind of shape. So so you can calculate these positions where the roots of a formula with a closed formula, and that's basically the best that you learn in school when it comes to, of course, you have curve discussion, things like that. But this was known very long time. Now, if you look at cubic formulas, then they look like that. And last time we already have seen that first of all, the first term is again a scaling, which narrows the function up and down. So we can just divide by that. If we cannot divide when it's a quadratic function, it's something we have seen. And by moving the function left in this direction, which is done by this, we can eliminate this term. So the term where we have a square number. This is something which works if you substitute E is equal to B divided by 3, and then you get new parameters there. This also has been long known. And so then we have a function of this shape, x to the third power plus px, moved up and down. And this function looks like that. So either you have no x term and you have this nice function, or you have this term where this term is positive. So then this point here has a slope which is like that, or you have a negative and the slope at this point is like that. So that's what you see. You can see at this position, you can see what's the slope here. Here it's +1, here it's -1, and here it's 0. And that's how you can classify these kind of functions. Okay, which is nice. Now you can go back to the 16th century and read the book of Cardano, How to Solve this Cubic Equation, which is it's a more complicated. I think it's 2 times or 3 times the size of the solution of quadratic formula. But there's a nice trick how to solve, and usually you bring this in this form and do another substitution for x, which transforms this into a quadratic equation. But what we need is an equation where we have a quadratic term on the left side and a cubic term on the right side, which is already a simplified form, because you could also have mixed terms of x, of y squared, and of y and x. But we are looking at this formula, which works modulo prime number, and which also works for real numbers. And again, we can simplify this by moving this to the left and right side, especially since we are not interested in the absolute values, but we are looking at the operator where we basically intersect this function with a line. Okay, so now we could have fun with, so let's see, with this function. So okay, so now let's start with something easy. We said b is equal to 0. Probably I can type in here the value 0. And a is now also 0. So here we see, in this case, zoom in. So here we see the cubic function, which is the green one, and the blue one is the square root of that, obviously. Now, if you so this function will be x to the power of 3/2. So x to the power of 3/2 and minus x to the power of 3/2. Now, this is not a very nice function because, whoops, hello, because we lost here audio. It's working again? Not yet, no. Let's see whether it records. So it is recording, interesting. So somebody found the audio button. Okay. I just reboot the system, maybe it works then. Okay, no, still not working. Huh? So it's still recording here, but it's not it's not, the loudspeaker's not working. Maybe it crashed. Okay, so you have to wait because that says, please wait on the screen. But it's still recording, so we can continue. Yeah, something happened. And maybe I'm back. Hello? It's back. Okay, interesting. Sorry for the guys listening to that. There's something going on with technology today. So, okay. So now let's look at this function. So x to the 3/2. Just write this on the slide. So if it's 0 and we have y is equal to x to the 3/2, so that's x to the 1.5. So x to the 1 is a line, x to the square is a parabola. So that's why this thing looks like a little bit like a parabola. So that's why it's sloped like that. That's the first thing. So if we are x to the 1/2 and we have a square root and a curve like that form. Now the bad thing about this is that we have this kind of edge, which is called a singularity at 0, 0. Singularities are bad for our purpose. So we want to have functions which are always nice and have a nice property. So that's something we don't have. So how can we get rid of this point? So we can move the formula slightly upwards and we get something like that. But I think we still have a small problem here at this point, which is a singularity here, which we don't like. So we need a good combination of factors which produces curves which look like that. Okay, so now this is the cubic function here. Here you can see the square root and the negative square root. And the first observation is by this form is you always have a mapped part. The upper part of the blue line is always mapped to lower part. So it's really symmetric function. That's the one thing. So if you look at this curve and you start more experiments, so it could be closed. It's not defined for all x, because at some point the cubic function goes to minus infinity, and as soon as you cross this point, you will lose. You don't have any solutions anymore. So that's why this blue line goes down like that. And something very strange happens if I put this to negative values. So then you could have something like that. But if I move this down, I get to some kind of hill, which looks like here. Here. So now I have the following phenomenon, is that here I have positive values and here I have positive values, and this nice curve is separated. So I have one part which looks like an island and the other one with this nice curve. So we can work with that. That's not a problem at all. We get into problems in the point when these two cuttits come together. So let's see. You have to. I have to slowly. So let's see. I have to type in the value probably. 0.3. No, 0.3 is too much. To make this maybe 1. And then this should have a closed form which might be at 5 maybe. No, 5 is too much. So I want to have this at, maybe make it more, 2, and a is equal 1. No, maybe it's I can calculate that point, but I'm just too lazy right now. So .05, something like that. So if I slowly get closer to it, I get some kind of curly curve. So which is here at this point when it can come here. When it's connecting, it's coming from here. It looks like that it goes up like there. And let's see, this should be at -3, and this should be something like 1.7, I think, and square root of 3. I think that's the solution here. But okay, you can plug it in, and when you get this curve, I think I have it on the slides. So this is also singularity which we don't want to have. Now, how do you decide whether you have a singularity or not? And for this, there is a formula. And so if you have this property, then you have a singularity. And here you can see what happens if you have a singularity, or this is the other case of a singularity. So this is the cases we do not want to allow. So we only take elliptic curves, and the idea is to use elliptic curves such like as a common domain, which do not have this property. Furthermore, we just make these examples for real numbers just to show how we can work within these elliptic curves, later on, we will use then modular prime numbers. Okay. So this is one example of a non-singular example which you have seen. Now the question is, what do we do with kind of elliptic curves? And the idea is the following. So if you look at these elliptic curves and you draw a line, so what happens if you draw a line is basically you're making a new equation. So you want to solve, you basically have on the left side, you have a line and you want to find the number of intersections. Now the thing is that if you have two intersections of this line, then there's always a third one with this curve. And this third intersection also has a very nice property, which we will find out later, which allows us to do some operations with that. Okay, so a line cutting this curve either doesn't hit it at all, it hit it once, it hits 3 times, or it could also hit it twice as a double root. That's also possible. And this is the thing that we want to do. And this brings us to the basic operation. So we define extension fields, there's a D missing here, in such a way. We look at a field with operation with plus and multiplication, and all the points in this field satisfy this equation. So, and this could be also modular prime number, but we just do this for real numbers at this point. Now, in order to solve certain cases, because sometimes you put the lines on that and you don't hit the curve, we introduce a new point, which is the infinity point. For this, you can think that the infinity point is if you go in this direction, then there is one point which is far apart in all directions. So it's not plus and minus infinity. It's infinity means something like way out there. Or you could think that this is like a globe, and the infinity is on the other side of a point 0, 0. So that means that infinity is not the same as 0, 0, but later on we give this empty set symbol for it because it will serve us as a neutral element for some operations. And the key thing is that we're looking is a star operator. So be careful that in some lectures or some notations it has some different name, but you introduce a star operator, but just to make clear. So given 2 points P and Q, we have these 2 points. We are looking for R, which is basically the next intersection. And this point should be uniquely defined. It is uniquely defined, so there's no fourth intersection, but we get a third intersection at most. But there's some situations which are complicated. So for example, consider this case that you have a point, let's say called S here, and you have another point S prime here, and they're just opposite of each other. Yeah. So where is the third intersection? So for this we need this point infinity, which is out there somewhere. So we can define this intersection. That's one problem why we have to introduce this intersection. Okay. So these are the operations that we're looking at. We have the star operator, and using the star operator, we will define a plus operator. And now the plus operator doesn't mean addition, but it works like addition somehow, because the star operator itself is not something which forms an abelian group. So the star operator will be defined for points which are in general position as the point where we hit the other point. So this is defined here. However, we could have that P stars P happens. So what happens if I have an element here and I have Yeah, I could have, let's say, an element here, and I want to have element star. I never practiced stars here as handwriting. So star, I cannot make a star, obviously. S. So what happens here? Now you would assume that this is the tangent and you get this point here. So that's the idea of S star S. So we have a tangent at this point P, and this will hit the elliptic curve at some other point. We need special rules like for infinity, and when we just define that this is the opposite point, and we need rules like that, but we get into this later on. And using that, we will define the plus operator, which we'll also look in later. Now, from a mathematical point of view, we're just interested in formulas. Yeah, so, and the formulas look nice compared to many other things. So if you want to compute P star Q, basically you have a lot of edge cases. So for example, if P is infinity, then you return the same value but with negative sign. If Q is infinity, you return the P value with opposite sign. But if they are not, if they are on the line and X is not equal to Q, so that actually that they are not put above each other, they have a very nice formula to calculate that. So that's this nice formula. And this calculates this point R. Now the funny thing about this formula is that you see the input, you see the output, but you don't see any parameter of elliptic curve. So it's it's not using the elliptic curve parameters here, which is nice. So you don't have to know the elliptic curves because if you, which is A and B, which is the parameters here, but you just can calculate it from this one. And other things which are nice is you have division, you have subtraction. Here you have to compute a square, and that's it. So these are operators which are also available in finite fields. Okay, so that's one thing. Now there's another case where now everything from this one, xp is equal to xq, and the points are, the given points are upon each other, and then now we have to find out what happens, which are these side cases, which look on the slides later on. But there's a very interesting case, what happens if we have the same input. And if we have the same input, we cannot divide by xp minus xq here, but then we get this formula. And in this formula, we have the only time where we use a parameter of this elliptic curve, which is A. That's the first time, and the only time we use it. So if P equals Q, then we have to use it, which is A. So that's the thing, and we get a different work for S, but if you look at this formula, then this formula is the same as this one if you substitute P and Q into it. So and xp is equal to xq and yp is equal to yq. Okay, so let's look why we get these nice formulas which do not use any parameters at all. And this is quite tricky, but it's not too complicated. But maybe we should look into the edge cases first. Okay, so what happens if P or Q equals infinity? Yeah, so let's start with the easiest thing. So what happens if I have infinity and infinity and I combine this somehow? There is no reasonable explanation to do so. So we have to define it somehow, and we define it in such a way that we stay with infinity point. Okay, so there's no formula to do so. If you have this infinity point combined by infinity point, nothing happens. Okay. More complex is a case that one of these values is not infinite. So you have this infinite point here, somewhere, and you have given a point here, and the question is, I put a line from this point P to infinity, where does it hit the curve? This question doesn't make sense. But you could find the opposite way. Now you could choose a point somewhere. Which point is not covered? And you find out that you can find always other points, but the only point that you cannot hit with the other points is the point on the opposite side, which is the point which has a negative y coordinate. So that's you have somehow a hole that you cannot reach, and that's why you would define that P and P star infinity produces this hole on the other side. So this point. So that's why we come up with this value, because it's the only place that we cannot reach. And for symmetry, you do also the other way around. Okay. Now with the same picture, because now we have another case. What happens if you have one point P here, and you have a point Q here? So this is one of the cases where you only hit the curve once, twice. And you never hit it again because there is no curve left. Also here in this case, P and Q. So what we do, we have to find a result from this operation, and that's why we introduce this infinity. So we assume this hits the curve again in infinity. So that's the other case where we have a special case and have to define it. So if you program that, you have to have some kind of special character which covers this infinity position. And this has been defined in such a way that it makes sense. So that operations work together and form an abelian group later on. So this is done on purpose. It's not something we can choose. Another case is that you have a point here. You know that all the points which have infinitive slopes are on the x-axis. So if you point here, P, and you want to calculate P star, I have to learn to make with stars. So some point P. You have the same problem here. If you look at the tangent will never touch it. So you would also define that if y is 0, that you go define this as infinite. Okay, so far so easy. So this is our operation which I just defined. The interesting question is how do you solve this system in an easy way if you have a general position? So for general position, the first thing that you do is you have P and Q given. And we want to describe this line. We can describe this line as a formal Laplace linear equation. You have y is equal to s times x plus d. Okay, and s, and this is something we need to know, is the slope. So it's the difference of y divided by the difference of x. So quite easy. D can be also calculated, but we don't need it, so we don't do it. So that's a good thing. So we don't need d at all. So we substitute this into this formula, and we get, so this is our formula, and we want to solve it, and we get this thing here. Okay, we know since the 16th century that we can solve it, and there's a general formula, and don't do that. Because it's a mess. It's a huge mess if you plug this into the formula. You can do this with values because there is a very nice trick. And that's really worth to know what the trick is working. So on the left side, we have now this values, which is a polynomial of degree 2. And on the right side, we have a polynomial of degree 3. And we know that every cubic formula has 3 solutions, xp, xq, and xr. So why did I call them xp, xq, and xr? Because we know that xp and xq are already solutions, because they're on the line in the first place. So this has xp and xq are given values that we already know. They are part of the solution. The thing we're interested in is xr. Okay. So what I do is I multiply the left side, put it on the right side, so I get this problem here, which is a polynomial which has exactly these kind of three solutions. Now, I can also write this polynomial as in this way, which is x minus xp times x minus xq times x minus xr. So that should be the same polynomial because it has the same solution and it has the same factor in front of x to the third power. So they should be exactly the same. So two polynomials are the same if the coefficients are the same. Now, if you look at the coefficient to x to the third power, then this is the same. Now, the next coefficient will be minus s squared. So that's the next one here. And here the next one will be minus xp minus xq minus xr. So this is the second coefficient. The second coefficient. And it should be the same. Now, the cool thing about the second coefficient is that we already know xp and xq. We already know these two. The only thing we're interested in is xr. So xr is something we put on. So xr is the thing we want to solve for, and so we put it on the right side. Now we have this equation: xr is equal to s squared minus xp minus xq. And s is something we have calculated on that side. So we already have xr. So here. So s is already given here. So we use that for a thing. And then we combine it in this equation. And then we have xr is done. We can compute xr. We know what is the x coordinate. So in order to compute the y coordinate, we have two possibilities. The first possibility is we plug it into the cubic equation. Don't, because that's a mess again. You plug it in the cubic equation, and then you have to compute the square root. Or, you know it's on the line. You know that this is on the line, and now you have this coordinate of xr. So you just get y coordinate just by knowing that you have that the difference, that the slope to xp and yp is the same. So that's a clever use of this equation that you have at hand. And so you can compute yr like that. So which is very nice and gives you a very small formula. You don't have to solve cubic equations and everything is fine. Now, what happens if p is equal to q? So p is equal to q. Then we cannot use this trick anymore, but what we can do is we can again define this function sx of t, which is where we use the slope, and the slope is defined as the derivative of this function. So if you take the derivative of this function here, you end up with this formula. We have a positive and a negative solution because you always have this mirrored image. So this is the positive solution and this is the negative solution. Unfortunately, there is a square root in the denominator, which we don't like. However, this is y. So we know we're given the point in x and y. So we can use yp. So this is yp at this point, yp. And this is also yp. For both solutions, you have yp in the denominator and even with the correct sign that you need. So you get rid of that. And now you have, for the slope, this simple formula which uses the derivative, but basically it doesn't use it anymore, but it just uses the coordinates. And if you have that, then you can do the same trick as before. And you just plug in that xp is equal to xq. And so you get a factor of 2 here. And here you can do the same thing. Second formula is the same thing because you also look at the relationship of the slope from the new point R to P. And that's also very nice. So we get a very nice formula in order to compute from the tangent with value. So, okay, so going back. So what you have seen is we looked in every case of this algorithm. Where is it? Here. We looked in every case of algorithm, and it's quite easy to follow how to get these values and how to calculate it. And if you look at this algorithm, it's very easy to implement. So it's not a big deal compared to solving cubic roots, which they have done at exercise. So this was just a warm-up, because that's not the operation we are working with. The operation we are working with is the plus operator. Okay, the plus operator is a star operator applied twice. Okay, so let's look at one of these. Assume that this is your cubic curve. I think that, so this, and now I want to do a P plus Q. So P plus Q, so I have maybe, this is P, and this is Q. So first I have to compute the star operator. The star operator is, I'm looking at this line here, going here. This basically this hits this point. That's by definition. So this point will be P star Q. That's this point. And then we have to do the star operator with infinity. So where's the star operator with infinity is that we map it on the other side. So this point here will be P plus Q. That's how we get this. So we have 2 points, we compute where the line intersects with the curve, and then we map it to the other side. So that's P plus Q. That's the definition. Obviously, it's not an addition. It's not a vector addition, just plus is just used because it has some property of plus. That's the only reason why I use it. And because we are used to plus and we want to have something like plus. And the interesting thing is that you can prove that this is an abelian group. And that means that you have all these properties. So we have, first property is that we have a neutral element. The second property is that we have an inverse element. So P plus, the neutral element is P. The neutral element will be infinity. Then we have P, and we have here we have P plus Q is the same as Q plus P. And this is the most complicated one. You have, so this is commutativity, and here you have associativity, so it doesn't matter in which order you do the plus operation. So for addition, this is straightforward. But for this operation, it's hard to prove. And the whole thing about this elliptic curves is that they found some kind of operation where these properties hold. And that was, they look in the literature, and actually the mathematicians came out with these properties before. They could say, oh, there's this nice abelian group. And then later on, the cryptographers said, okay, well, let's take it and do some cryptography. So it's like going to a nice body of mathematics and looking everywhere in order to find interesting groups which can be harnessed in order to make a cryptographic scheme out of that. Okay, so this was commutativity, and this is associativity, but I don't have time for writing FF3. Okay, maybe we can see whether these operations hold. So, and to warm up, what does it mean? So if I do for neutral element, if I have P plus the neutral element, probably neutral element, we don't know yet, the infinity, then this is defined as P, and then we have star infinity star infinity. So what happens if P star infinity, what do we get? Make another P here. Let's say this is P prime. So what happens if I do P star infinity? More than nothing, we just map to the other side. So that's P star infinity. Okay? So, and what happens if I do this again? I come back. Okay, that was easy. Could have been easy, if you would have remembered the rules. Okay, so that's a fine thing. Now this is more complicated. So is there an element that you get infinity? So that P plus Q is gets you infinity. Oh, let's look at some element. Let's look at so P plus Q gleich infinity. Let's look. So P plus Q is the same as P star Q star infinity. And the question is, how do I make this infinity? Yeah. So what value should I have here at this point that something star infinity is infinity? Which value star infinity is infinity? Well, infinity is the neutral element, so it must be infinity. So if I find an element combined with some other element which gives me infinity, I've solved this problem. So for this, and let's assume I have this value here. Let's say this is P prime prime. So which value gives infinity? It gives the opposite element, which is here in this point here, which is Q prime prime. If this is on the other side, and I just flip the side, I go to infinity. And so the inverse is just flipping the y coordinate. Okay, so that's also solved. For the commutativity, we can use the fact that, so we already know that the star operator is commutative, because what we do is we define the line by P and Q. So it doesn't matter which line we define, or from P to Q or Q to P. So that's already given. And so if we have that, then this also follows, because you have the same value, star operator infinity, and you get just the flip ones. Okay. Now that was easy. Now the complicated thing is this thing here. And so there is a theorem which is called the 9 associated points theorem, and it has to do with the structure of cubic functions. And this would take some, let's say, 60 to 90 minutes to prove this in this lecture. And I have a colleague who has done it, and I uploaded his lecture notes into the Elias in case you are really, really interested in the proof of that. But I don't think that this gives us anything further for cryptographic tools. So I'm omitting it and give you now the break to look it up yourself.